seminar sponsored by our USC TCORS. I'm really pleased to introduce Pamela Galt, who's a Monell Chemical Senses Center. What that means is she knows an awful lot about things that we don't know about related to flavorings and sensory responses and how taste and olfaction work. This is a topic of great interest to us because of the widespread use of flavorings in electronic cigarette products. I will say that in meeting Pamela in a number of meetings now over the years, I'm always impressed by sort of the very interesting work that they do at Monell, which is Penn affiliated but a freestanding research institute that is directed at Senses. So thanks so much for coming, and we'll do this very informally. We have a lot of time set aside to talk.
Yes, so please stop, ask questions, comments, whatever. I mean, this should be interactive, not just a lecture. Okay, so that's my preference anyway. So I was asked to come here, and hopefully we can find some synergy with what you folks are doing and what the kind of work we do here at Monell. We have recently started to think about how smell and taste interacts with, the products that are increasingly being used, particularly among youth. And obviously some of this comes out of the regulatory interest in flavors in e-cigarettes, which we know starting early on in this saga that there was a preference and use of sweet flavored tobacco products in cigarettes by young and beginning smokers. And that led to the Family Smoking Prevention Tobacco Control Act in 2009 that banned all flavorings from tobacco products with the exception of menthol, and this is exactly what they were talking about. Now, I get a lot of people asking me, what does it actually mean to say that it's a characterizing flavor of the tobacco product or tobacco smoke? Basically, I think people have come to believe that that means that it provides some sensory benefit above and beyond what the other components of the tobacco product are. And so, other than tobacco flavorings or menthol, those were banned in tobacco products as of 2009. But of course now, sweet flavors have been used almost exclusively in e-cigarettes, particularly among the youth market. And although the FDA extended their authority to include e-cigarettes, they really had almost a nothing statement on what to do about flavorings in e-cigarettes. And I was conjecturing that that really is because there's a lot of uncertainty about what flavors are, how they contribute, and all of those things. So our interest in flavor compounds in electronic nicotine delivery products is really in two areas. One is how the sensory appeal of added flavors impacts the youth and beginning users to initiate and continue using these products. And a sort of complementary area of interest is what are the respiratory health implications of inhaled flavors. And I'll present some data on both of these, but I just want to caution you that with us as well as many of people studying this issue, there are more questions than answers at this point in time and a lot of intriguing areas to explore. So obviously we know that the flavor world is immense in terms of what is advertised and available for people either purchasing it pre-filled or buying their own flavorings and mixing them themselves. So let's just talk about flavor, for example, for a minute. Flavor is a complex multisensorial experience. Most people, when they think of flavor, they talk about the taste of something. And flavor, because it usually comes in the form of something that is ingested, either liquid form, solid form, or in the case of smoking, oral consumption. The experience is localized to the mouth, and that's why people talk about flavor as largely being taste. But in fact, we have very limited ways to experience taste sensations. We have the 5 basic tastes: sour, salty, sweet, savory, umami, bitter. We also may have some fat taste receptors or starchy or mineral taste, less well characterized. But the taste system is really very simple compared to the olfactory system. The olfactory system, and particularly when we eat or drink something or inhale something, it is the retronasal olfaction, what goes from the back of our throat up to the olfactory receptors in our nose, that actually provides us with the information to tell us what we're smelling, drinking, or eating. You can do this yourself at home or anywhere. Just take something like a jelly bean, put it in your mouth, close your nose, chew it up, and what you'll get is sweet. But you won't have a clue as to what flavor actually is in there. Release your nose, and all of a sudden, if you're chewing a strawberry or a lemon jelly bean, you will immediately get that identifying information. We think that in terms of those two sensations, that flavor is probably more like 75–80% of olfaction rather than pure taste. Taste gives you these basic qualities, more or less of each of them, but olfaction is where the incredible diversity of the world comes in. Flavor is also composed of somatosensation, what we call mouthfeel or sensate chemesthesis. It's the pressure, texture, temperature of a chemical solution that goes into the mouth, either inhaled, swallowed, etc. So it's many different things, and cigarette products provide stimulation in all these areas, taste, smell, and the sensation of the mouthfeel as well. In fact, some of that is what people actually like about, is that mouthfeel, that sensation that they get in the throat and the oral cavity. So it's complicated at this point already before we talk about flavors. We're talking about three distinct sensory systems that nonetheless have a lot of overlap, complement each other, are highly integrated in the brain so that they come across as one sensation, unimodal sensation, when in fact they're not. So when we look at the kinesthetic innervation of the respiratory tract, we have first of all the olfactory nerve, which is transduced by receptors that reside right above the cleft here, right above the bridge of the nose. Very limited area, especially compared to rodents, which just makes it hard to compare animal data with human data, because a mouse will have olfactory receptors all over their nose, where we have it in a very specialized area. We also have the trigeminal nerve, which is largely responsible for the irritant sensations that we might get from things like tobacco smoke, nicotine, other combustible compounds in that. And then further down the respiratory tract, we have the glossopharyngeal nerve, which is in the nasopharyngeal area, and the vagus nerve. And so these are all chemically sensitive fibers that respond to irritants or odors in the respiratory tract. And we're learning a lot more about the ligands for these specific receptor cells on the trigeminal nerve in particular, which seems to be the first area which will initiate reflex apnea or irritant responses that are aversive. So what impact do flavors have on the sensory profile of e-cigarettes? My colleague and I, Paul Wise, have been doing some work on this for the last couple of years. And it seems that they may contribute indirectly by enhancing or reducing the sensory properties of other ingredients. So we're talking about here, when we talk about the nerve system, the trigeminal nerve, we're learning more and more that there are specific receptors that mediate these chemosensory responses to irrigant ligands. And so we have, for example, TRPV1, which was first identified as the capsaicin receptor, the one that responds when we experience the burning of chili peppers and that sort of thing. But it's also involved in transducing the response to a lot of other irritants. TRPM8, which is also temperature sensitive, responds to things like menthol particularly, as well as other compounds like citrol or linalool, which are used in flavors and fragrances quite all the time. And TRPA1, which is probably the most promiscuous of the TRP channels, responds to many other compounds, but ostensibly one of the important ones are the irritants like nicotine, acrolein, and formaldehyde. So basically, we have a specialized chemosensory system that responds to many different compounds individually and needs to be understood better in order to understand what the downstream response after these TRP channels are associated. And I'll talk a little bit more about that later. So of course, one of the adverse responses to tobacco products is the sensory properties of nicotine. Now, the trigeminal system responds to multiple irritant compounds depending on which of these ion channels are stimulated and the ligand for it. Nicotine is a very potent airway irritant. It triggers these sensations through the TRPA1 receptor. And it's also a bitter agonist, which is also interestingly. And the sensory properties of nicotine alone can be sufficiently aversive to actually either discourage initiation among youth or young users or the maintenance of e-cigarette use. But that's where the flavor compounds come in. They may actually be working to mask or ameliorate some of these aversive sensations from nicotine. Now, menthol is still allowed to be in traditional tobacco products, and we know a lot about menthol because there's been a lot of epidemiology work looking at the health effects. But basically, what we know from the sensory effect of menthol is that it does desensitize the response to some of the more aversive properties of tobacco smoke or nicotine. So this is an animal study that was done a few years ago showing that pre-exposure to nicotine, addition of L-menthol, to a acrolein, which is a TRPA1 ligand, essentially abolishes the irritant response to an irritant. So it essentially is masking it at a way, probably binding into some receptors that are making the sensation of this irritant less aversive. When we took that into a human study, here we were looking at the irritant response to acetic acid in a psychophysical way where we actually present the chemical to one nostril at a certain concentration, clean air to the other. One of the fascinating facts about the nose and the olfactory system is that the olfactory system can readily detect chemicals at very low compounds, but it will never tell you which nostril is being stimulated. So you cannot lateralize a pure olfactory sensation. You can put the odor in one side of the nose and it's combined. However, once you reach the irritant threshold, you get to that concentration, then you have location information because those receptors are responding and telling you which nostril is actually being activated. So this was used by a colleague of mine many years ago to develop this method to understand when a chemical becomes an irritant. And as you can see, if you pre-treat the nose with L-menthol, you actually see that the response to acetic acid is less sensitive. People can tolerate more acetic acid after a couple of sniffs of L-menthol. So it's a very potent masker for a lot of different irritant sensations. We also have looked at this in terms of our model where we look at cough reflex response. So here we just use a medical nebulizer to control the inhalation rate and use a dosimeter to control the delivery. Generally what we're looking at is the capsaicin cough reflex and how that's modulated by different compounds. And it turns out that menthol, first of all, desensitizes the cough reflex threshold. So pre-treating with menthol makes individuals less responsive to an inhalation of capsaicin, and they will not cough at the same concentration that they would have coughed when they didn't have the pre-concentration of menthol. What was interesting in this study was that my colleague Paul Wise decided that he also wanted to look at a taste compound to see if that would change the response. And indeed, as you can see, the cough threshold to capsaicin was actually reduced when people rinsed their mouth with sucrose solution prior to that. And so this got him thinking in particular about the e-cigarette compounds, the flavor compounds, which are very sweet and might actually be masking some of the aversive response, or what we would consider the respiratory reflex, the protective response of the airways to a known irritant. Now, when it comes to sweetness, children and adolescents are particularly vulnerable, and we believe that this is adaptive because this is a period of enormous growth And food sources that are sweet are usually highly caloric and nutritive. So there's a biological imperative for children that are growing and adolescents that are still continuing to grow to essentially crave sweet compounds, which does decrease as adulthood increases. And what's interesting from this graph is this was taken from a study by my collaborator Julie Manella, who studies a lot of taste responses in children. Is that even, she repeated this study over a 10-year span, and even though the actual daily sugar intake of children and adults reduced significantly over that period of time, it didn't change their sweet preference. In other words, how much sucrose they liked in a particular solution. And children like way more than adults. I mean, we would probably cringe if we taste the solution that most children and adolescents crave. And again, this does seem to be a biological imperative. So we're working against a very strong system when we want to take sweet flavors away from children and adolescents. Yeah.
Clarify, when you're looking at years over time there, is this the same population or?
No, it's a different population.
So these are population-based studies of?
Population-based studies, yes,
Okay.
yes. Yeah, these are 400 children and their parents, one parent in each case, over a 10-year span looking at the same essentially experimental protocol. And so it's a tracking method where they're given different concentrations of sucrose solutions and asked which is their preferred one, and they go back and forth and track it over time to get to the point where they get what's called the bliss point for everyone, which is this is the solution that makes me the happiest, that I like the best. Yes.
Thank you.
Yes.
Bliss.
So anyway, it's really important to understand that is that sweet is powerful. It's really powerful for a lot of reasons, but it's especially powerful, and children and adolescents seem to be especially susceptible to its influence. It's also the case in this study that not only is it much preferred, but it's highly effective in reducing bitterness. And so you can see that of all the bitter agents that were tried for both children and adults, sucrose was the most effective at reducing the bitterness of caffeine, quinine, denatonium, which is the most bitter compound known to man. That's the Bitrex that they put into products to keep people from ingesting it. And probe, of course, which is the quintessential bitter one that actually has a genetic basis for it. So given all of this, it stands to reason that they're increasing the sensory appeal of tobacco products, and particularly e-cigarettes. It's also the case that this works even with just sweet aromas. So here we have a fruity aroma, ethyl hexanoate, that was used as a sort of prototypical fruity sweet compound. And when you add it to a sucrose solution, it turns out that it actually makes the sucrose solution be perceived as sweeter. So the aroma, having been associated with sweet in terms of the natural food products that one eats, actually can enhance the actual sweetness of a sucrose solution. So there's a synergy there going on, and again, this is not happening necessarily in the oral cavity in the nose, but it's happening in the brain. There's the prefrontal cortex is very much involved in this multimodal sensory integration. It's also the case that it appears that these sweet-smelling aromas like ethyl hexanoate or vanillin might also change the bitterness of a bitter solution. This is a bitter solution that's used in studies, sucrose octoacetate, and it's not a huge effect, but it still was a consistent effect. People rated the bitterness of this solution as less bitter when it was paired with the sweet vanilla or the ethyl hexanoate. So there's a lot of interactions going on between taste and smell here in terms of the ability of smells to actually increase sweetness of solutions and also reduce bitterness. So again, what impact do flavors have? Well, my colleague Paul Wise recently completed a study where he was looking on the enhancement of the taste mixtures of just the matrix in e-cigarettes, vegetable glycerin and propylene glycol. Both have a tendency to be a little sweet, and PG seems to have a slight bitter note in it as well, which may be related to its purity, perhaps. He looked at one commercial flavor blend, strawberry flavor, and as you can see here, and I'll show you later, it's not a single monomolecular compound. It's a mixture of an aldehyde C16, which is probably the prototypical strawberry aroma, but others as well. And so he took these particular compounds out of there and decided to look at them in terms of being sweet aroma. Ethyl butyrate is sort of pineapple, isoamyl acetate is the banana odor, and vanillin, and then ethyl maltol, which is more in the caramel, which has become a very popular. So we have model fruity aromas, model more dessert-associated aromas. And then he also looked at a couple of other compounds, menthol, which is not really sweet, but obviously the most common cigarette flavor, and a burnt or bitter note, which was the negative control. It wasn't expected to enhance sweetness. In this experiment, he had 9 different stimulus conditions with increasing aroma strength or increasing taste strength of the concentration of the PGG solution, or the no aroma, or the weak aroma, or the moderate aroma. And basically, people were just asked to rate. They were provided this. It's important to realize that the aromas were presented to the mouth as odorized air with clean air as a control, in parallel with dripping the PG-VG solution into the mouth as well. So how it would be experienced only in the oral cavity and through retronasal olfaction. There were 20 people in the study, men and women, young. They were not current users of tobacco products, since we weren't providing them with a tobacco experience. That didn't matter in this case, but they had experimented at least once with a tobacco product. And so it turned out that the model fruity stimuli, the pineapple or the banana, actually increased the rated sweetness of the PG-VG solution probably about 35%. So the dashed black lines represent the clean air control, and you can see the blue line represents the low flavor, and the red line represents the high intensity flavor. The confection, the vanillin and the ethyl maltol seem to increase the rated pleasantness of the solutions as well. So there is clearly another effect here of just adding these fruity or confection aromas to the matrix, apart from any other constituents in the cigarette. So this is, of course, no nicotine exposure. And as expected, the menthol and the burnt odor, isovalproate, had no measurable effect on any of the ratings. So it seems to be that fruity and sweet associated aromas are the ones that are having the biggest effects, which from a biological standpoint is what would be expected. So clearly, he seems to have established, and other people have as well, that the flavorants do affect the perceived taste of the solvents used in e-cigarettes, which is potentially important. They increase the pleasantness and possibly decrease the bitterness as well, which is consistent with making these solutions increasingly palatable. It seems that there are differences among the flavor compounds, the aromas that are used. They may have very different sensory-specific effects. Again, so many out there, as you'll see, yet to be investigated. This is probably not the right approach to doing it, but one has to start somewhere, at least establishing the phenomenon and showing that there is an effect of this. Obviously, if you see this in actual products, they can contribute to a more sensory appeal of the product and lower the barrier to initiation and continued use. But what's interesting is the impact of aroma on other sweet stimuli seems to mirror the effects that we see for sugars and non-nutritive sweeteners. So aromas are having an effect, even though they're not being ingested. There is no nutritional value from smelling a sweet aroma, but somehow they have taken on the value, the reward value of the sweet tastes and what would be the sucrose and obviously the downstream effects from the sucrose ingestion. So now I'll just stop and let you ask questions about that part of the presentation.
If you were to vaporize these solutions, would you expect any of the sensory effects of the compounds to change?
In terms of the PGVG solution?
Is it right that you were just orally administrating?
Yes, it was just being dripped as a liquid.
So if it were like as an e-cigarette, or would you
Mhm.
vaporize,
Mhm.
would you expect the sensory effects of the like sweet compounds to actually change?
I think they could potentially even be more effective if people weren't experienced. I mean, I think probably there would be less bitterness because it would have to come from deposition from the aerosol. So I think the sensory effects of the aromas might even be greater with an aerosol delivery of the PGVG solution rather than simply a liquid delivery. And it's artificial, obviously, but it was the first step in doing that kind of a study. And it also mirrored the effects on the sucrose, how the aroma increased the pleasantness of the sucrose solution. And we know, for example, that if you look at the chat rooms from some of the mixologists that are, putting vaping solutions together, many of them will say that they are adding sweetener to the solution as well to mask some of the flavor of the matrix and possibly even when they use nicotine in there. So it's a very complicated synergistic effect, absolutely.
So just a question, maybe we'll come back to this later, so I can see sort of big tobacco doing experiments and understanding what's going on. In terms of the larger e-cigarette industry, the vaping industry, you're talking about the mixologists. I mean, do you think it's just sort of intuitive that they've learned through experience, or do you think there's reference to the scientific literature and understanding, or do we have a clue?
I would think not. We have talked to and interviewed some of these folks, and mostly it's sort of personal connections. They learn about this. The major flavor and fragrance companies do not publish their formulas. Those are proprietary for them. That's something. I mean, they will tell you what's in there, but they will not tell you what the ratios are basically. So it's a trial and error, sort of experience for these people. They will try them and adjust them accordingly. So there's not really a reference. There, I'll show you in a minute that there's literally, how should I put this? Okay, so this is from the Sigma Aldrich catalog, and if you just go through and look for the characterization, the quality, if you want a caramel odor, there are 43 chemical compounds identified that contribute to that in one way or another. For citrus, and that obviously includes grapefruit, lemon, and lime, it's 124. For apple, there's 118. There are that many different. I mean, I have a refrigerator filled with aroma compounds from many of the industrial sponsors that we have, or those that I've purchased. I probably have 20 or 22 different apple scents. I mean, it's just, green apple, living apple, red delicious apple, granny smith apple, they all have a slightly different sensory profile, and they have a slightly different sensory profile because they either eliminate or add different chemical compounds. So it's, it's wide open.
Naive question, what is the Sigma Aldrich catalog?
It's a chemical distributor, essentially. Yes, yeah. It's commercial, yes. And they have a they have a flavors and fragrances catalog. And as you probably know, these are chemical compounds that are considered GRAS, generally regarded as safe. But of course, that has been tested only in ingestion, not in inhalation. So that's where, this is, and of course this has been done before, obviously. I mean, people have been smoking hookah with flavors for years, and traditional tobacco products had these flavor compounds in them. But I think nowhere have we seen the concentrations of flavors at such high levels as before e-cigarettes came into use. So this is just an example of why the world is in terms of that. Now, any of these, berry, cherry, you can find one compound that's sort of prototypical of many of these, but most of these flavor compounds are much more complex than that.
Actually, on the concentration thing, so in terms of, let's say, a cherry Coke versus a cherry e-cig, what is so there's something making it taste like cherry.
Right.
I mean, would the concentrations be comparable in the two? Do we have any idea about?
Well, I think in terms of the concentration in the liquid, you probably have a slightly higher concentration for ingestion than you would for inhalation. The olfactory system is much more sensitive. You really don't need to put that much in there. But there is, there's still more than there has traditionally been into regular tobacco products before they were, before the FDA restricted it. That's certainly the case.
Pamela, sorry.
Sure.
Sidetrack.
No, no.
You mentioned the GRAS restrictions and testing standards. Is there anything like that for things that we inhale?
There is IFRA, which is the Institute for Fragrance Research Association, that's worldwide, and then their scientific arm is called RIFM, Research Institute on Fragrance Materials. Now, they obviously, some materials are both fragrances and flavors, so they cover some of that, but not specifically. FEMA is the Flavor Manufacturers Association, and they're the ones that issue, essentially the expert opinions on the GRAS labeling. But in terms of inhalation, there's nowhere near the amount of data that there should be on the inhalation of even compounds that are not flavors.
And there's no, put aside the workplace, there's no standards. There's no indoor air quality standards.
There's not even any, RELs or anything for, community exposures on these compounds. There's some low-hanging fruit out there that has been studied extensively and not gone beyond that. So it's really, and again, there aren't, for some of these effects, there aren't really good cell or animal models, even for the inflammatory response, unless you want to move directly to, whole animal studies, inhalation studies, or humans. So I just want to talk a little bit about, the respiratory health issues, the other piece of the puzzle that we look at in terms of Monell's interest in this area. Because the chemically sensitive systems in the airways are responsive in both positive and negative ways to many of these compounds. And we've been looking at the ligands for these trip ion channels and also the solitary chemosensory cells, which seem to be the sentinels on the cilia of the trigeminal nerve dendrites that are actually producing the response to many irritant compounds. Also, I'm going to talk a little bit about how taste receptors, and when I say taste receptors, I'm talking about the same type of receptor outside of the oral cavity in the airways is involved in innate immunity. So, are the flavor compounds GRAS in the airways? As I said, the Flavor Extracting Manufacturers Association has been evaluating flavor safety for a very long time. They do expert panel, but they're very clear if you go to their website that this is only for the intended use, which is food flavor ingestion. And they say completely, panel does not evaluate flavorings for use in products other than human food or products involving routes of exposure other than ingestion. And I know from speaking to many of them, they would be very happy if none of their flavor compounds were used in these products, but they don't have control over that. So they put that in there as a way of saying it's not my problem, but it is their problem in many respects. So we know that there's a lot going on here with, and where do you start? Do you pick a prototypical, berry cherry kind of model compound to use, a fruity one? It's going to be very difficult to sort of find our way through this morass of many chemical compounds that constitute flavor. And some of these are going to taste as well. It's not the case that something that smells like chocolate is going to taste sweet. It could be a little bitter as well, which is why they add sucrose or other sweeteners to the e-liquid to counteract that. So back to these TRP channels, the TRP channels that mediate the chemosensory response to irrigant ligands. We're very interested in this because it seems that there's a lot of specificity in the system, and there may be a lot of ways to understand how the irritant response is occurring. This is sort of a little schematic of how these solitary chemosensory cells are involved in the neurogenic inflammation and immune response and the airway protection reflexes. They seem to be the ones that are actually specifically responsive to different chemical ligands, which part of the trigeminal nerve transduces this response. That's when we feel burning or prickling or stinging or irritation. But once these are stimulated, they also stimulate other pathways. So you can have inflammatory responses such as cytokine release, substance P, and other peptides that are released that can set up a chronic inflammatory response in the airways. And this is something that could eventually lead to things like mast cell degranulation, and so on and so on. So my colleague, Marco Tizzano, who recently joined Monell last year, was involved in the identification and discovery of these specialized chemosensory cells that are found throughout the airways. And some of their responses are less than let's say non-intuitive. So one of the major findings of the SCCs in the lungs is that they respond to bitter compounds. And that seems counterintuitive, why would you have that response? And in fact, their response to bitter compounds is a positive one. They produce bronchodilation, not bronchoconstriction, which one might expect, at least in acute exposures. At this point, we don't know about continued exposures and what that might do. But basically, this is a new way of understanding how the airways respond to irritants, different ligands. Now, there's been some look, mostly in cell cultures, looking at inflammatory responses. So this is a study that came out last year from the Chu laboratory. Basically, what they were looking at is IL-6 production in human airway epithelial cells to e-liquid solutions with no nicotine and e-liquid solutions containing nicotine, both at 24 and 48 hours after exposure. And you can see there's quite a nice dose-response function going on there with IL-6 production. Again, these were tobacco-flavored e-liquids, not fruity flavors or anything like that, and it's typical PG/VG concentration. Although, again, what is going into tobacco flavor is not specified. Most of the studies that have been done thus far talk about the flavor as a unimodal compound that has been put into the e-cigarette without actually identifying what chemical might be triggering a particular response. And that's something that I know when I spoke with Jessica earlier, having the e-liquids actually analyzed for the individual constituents rather than just identifying the flavor profile of it is very important if you're going to understand what might be the bad actor in the mixture at that point. And Mashi in the group up at in Buffalo have looked at this in human bronchial epithelial cells as well. And these were different compounds, different flavor compounds. Again, not specified what the constituents are. But interestingly, he seemed to find that tobacco and coffee, if you can look at that, this is, okay, IL-6 production was highest to the coffee compound, IL-1 beta, and IL-10 to the strawberry compound, although coffee was also, elevated as well. And it seemed like all of these, except for the air exposure, all of them decreased the cell metabolic activity and cell viability. But again, these were commercially available e-liquids purchased from various vape shops in Buffalo and not otherwise characterized. So what's in the strawberry solution, what's in the coffee solution, we don't know. But in this particular kind of a cell-air-liquid interface system, they do seem to be producing an inflammatory response.
Why is the metabolic activity decreasing in the flavorings?
They did not conjecture why that was happening. They seem to be a little surprised by that, actually.
John, do you
Yeah.
have any thoughts? I mean, if you took it far enough, does
Yeah.
that mean with the increased metabolic activity that there might be some people who have heightened risk for obesity?
Yes, no, sure.
So if you have people who are using tobacco products, and especially with women who try to use tobacco products
For weight
for weight control, and you have tobacco products that are flavored, does that have an opposite effect to what they're trying to achieve with weight control?
It's a very interesting question.
Well, cells are higher.
Yeah, right. But, yeah. So, I mean, these are beginning investigations into the inflammatory response and the viability of airway, cells. And so, again, this is a start, but nobody really knows exactly the best way to investigate some of these problems and these compounds. I recently was asked to do a study on propylene glycol, not for e-cigarette users, but in propylene glycol manufacturers, because the European Chemical Agency had a dossier submitted that wanted to classify it as a respiratory irritant. And there was no real evidence one way or the other, except from mixtures of PG and other glycol ethers in theatrical smoke, that there could be some irritation in the airways from that. So we actually did controlled exposure studies just to PG aerosol vapor on 20 individuals, both males and females, and screened them for obviously normal pulmonary function. But there were 3 exposures: 20 milligrams per cubic meter, 100 milligrams, or 200 milligrams. And there were 4-hour exposures to the lower doses and only 30-minute exposures to the higher dose. And when I show you the chamber, you'll understand why that was. We got a very specialized fog generator from a company that was customized to deliver the droplets in the respirable range, which was important for this study, and control this in our chamber. We also had an optical density monitor system and a particle sizer going to ensure the consistency of the exposure in the chamber, and that was linked to a software program that controlled the exposure and kept it at a relatively constant level. So this is the chamber looking in clean air. This is 20 milligrams exposure. This is 100 milligrams.
You actually have people to
And that's 200. Now the 200 was only 30 minutes, and to be safe, we sat them on the exercise bike so that they didn't have to find it in the mist, because otherwise I think they would have slid around the room a little bit.
Did you have to take a shower?
We put our subjects in scrubs and hairnets and things like that, and they were allowed to take their smartphones in there in a case so that it wouldn't get, because the PG will deposit on the surface. It will evaporate eventually, but it does get a little slimy at first, so yes, yeah.
Pamela, can I ask what causes it to be more opaque? Is there something about the propylene glycol?
The density of
Just
the
density.
droplets, yes,
Okay.
yeah, is the density, yes. Yeah. So basically, we found no effects on pulmonary function for any of the exposures. There looked to be it's not a significant decrease on the FEV1, FVC, but that was in the lowest exposure condition, so it really didn't make sense, particularly since the 100 milligram exposure for 4 hours showed absolutely nothing.
What was the size of the part?
Between 2 and 5, yeah. What we did find, though, is that, obviously people didn't love the exposure, although everybody stayed in there. We had no real complaints. But what they did report on was dryness, okay? And this is something, it's very difficult to get people subjectively to tell you about sensations in the airways. But what we did is we had diagrams where we allowed them to color in how much experience of irritation or dryness they were feeling in the nose, in the nasopharyngeal area, in the throat, and elsewhere. And you can see it's not much, but there is a dose response for the drying effect. And basically what that seems to suggest to us is that if you know anything about PG and you've been on an airplane, it's what they use to de-ice airplanes, because it's hygroscopic, it absorbs the water, okay? So it's doing the same thing to the respiratory tract. In fact, I did this experiment myself because I would never put anybody in an experiment that I haven't experienced. But what I found is, particularly at the 100 and 200, I had intense rhinorrhea because the nose was trying to compensate for the dryness. So we put a big box of Kleenex in the chamber and allowed people to wipe their nose, and we counted the Kleenex at the end of each exposure to sort of quantitate how much rhinorrhea they experienced. However, this suggests that PG, although it is not a respiratory irritant in the sense that it is stimulating these SCCs and transducing an irritant response, it may be having an indirect effect by its drying potential on the airway epithelium, which may render the SCCs more sensitive to the other irritants that are potentially in e-cigarettes.
Just speculate on what the concentration would be.
In an e-cigarette?
Yeah.
Yeah, we're thinking it's probably closer to the 100 to 150 milligram exposure. There's not many studies looking at that, but we've seen a little bit of data on that, and we've been trying to suss that out for that reason alone, yes. I mean, these are obviously high concentration. I mean, the AIHA wheel for PG is 10 milligrams, but there's no OSHA limit for it, so nothing is, in sort of a regulatory arena. But people who de-ice airplanes usually don't use any respiratory protection, and people in, theater productions can be exposed to these kinds of high levels. So there is an effect of PG, but it's not a direct irritant effect, but it might modulate the irritant effect because by drying the epithelial surface and the airway, you may be making it more susceptible to the other irritants that might be present in e-cigarettes. Just want to spend a minute or two talking about this because it's a new area of research that has emerged at Monell recently, is how these taste receptors, bitter and sweet taste receptors, are actually found in the airways now. It's not that the airway is tasting it, but it's responding to chemicals. And these bitter receptors, of which there is great genetic variability, which we were talking about earlier, because understanding individual response to the initiation and maintenance of the use of these products may depend somewhat on the genetics underlying taste and smell responsiveness. So these bitter receptors are expressed in these solitary chemosensory cells, and they respond potently to chemical irritants. The bitter receptors in the nose appear to protect against bacterial infection. What they do is they stimulate the production of nitric oxide, which is a clear bactericide for, people who have chronic sinusitis have extremely low levels of nitric oxide in the sinus cavities. And that's thought to be a problem. And that's really where this came from. It's one of our ENT collaborators, Dr. Noam Cohen, who is trying to understand why some people who have chronic sinusitis respond to treatment and other people don't. And this it seems to have something to do with their genetic differences in bitter receptor production. So these T2Rs are in human noses and also in human airway smooth muscle. And they detect bacteria, and when they're activated, they increase ciliary bead frequency and mucociliary clearance. So they're actually flushing things out of the airway, the nose and the airways. And it turns out that there are sweet receptors also co-located within these solitary chemosensory cells, although their function is less well known than the bitter receptors. What's interesting is that when these cells were treated with either glucose or sucrose, it inhibited the bitter response of calcium signaling, which is actually a protective response. So sweet things that are inhaled into the nose and the airways are disrupting an innate immunity in the airways. And that seems to be an unknown consequence of some of these inhaled compounds that might be important for understanding. The bottom line is you can see here, I don't have a pointer with me, but these are different concentrations of glucose control, and this is the calcium response, and you can see the calcium response is going down as the sweet concentration increases, okay? And here, what you see in blue, lactosol is a sweet blocker. And so if you pre-treat the system with lactosol or co-exposure to lactosol and glucose, you essentially wouldn't experience sweetness. It's really unpleasant, actually, but basically what you can see is if you block the response with lactazole, you get the response, you get the immune response back. And here is just looking at different concentrations. The control here obviously is fine. I have millimolar of glucose, 1.5, all the way up to 5, and it goes down in a very continued fashion. You block it with lactazole, it rebounds, and this is sucrose as well here, showing the suppression of these bitter receptor responses to a sweet compound, and you can block it with lactazole again. So this innate immunity, this production of ciliary beat frequency, mucociliary clearance, as well as the production of nitric oxide, seems to be disrupted by the exposure of these airway cells to sweet compounds, which may be another feature of the health response that comes from inhaling sweet compounds into the airways. So what we're looking at, hopefully, is still looking at the impact of these flavor compounds on the sensory profile, either its ability to reduce irritation and increase appeal, particularly to youth and novice users. We think that this is playing an important role, and model compounds, as we said earlier, trying to figure out which ones to test or understand is still in the very infancy. We've looked at some flavor compounds with Andrew Strasser at TCORS at UPenn on the patterns of use and smoking topography. That work may continue with them and not with us. We're also really very interested in the potential of these flavor compounds to have adverse health impacts on the respiratory tract, and importantly, understanding the role on these extraoral taste receptors and the solitary chemosensory cells in disrupting what is essentially a protective response of the airways to inhaled irritants and other agents and bacteria. And I will stop there and ask that you ask questions and discuss this. Thank you very much.
Oh, thank you first. Some of the TCORS group studies ads and communications, and I'm wondering, there probably is a perception out there that sweet flavors and menthol are protective. And these data suggest the opposite.
Exactly.
So I'm wondering, for those people who still want to study marketing and communication, how we would fashion messages that would get at the fact this isn't what you think it is when you think you're taking sweet flavors and they're less dangerous or not dangerous at all compared to bitter or non-flavored.
Yeah, I mean, obviously we don't know. I think it's important to recognize that in all of these studies that have been done with cell line looking at responses, the response to these flavor compounds is, the inflammatory response is less than it is to traditional tobacco products. They don't seem to be as harmful, at least, in producing this inflammatory response. But they are still producing an inflammatory response. So even though the degree of harm may be less, that doesn't mean that there is no adverse effect on it. And how do you, sure, something, as I said, I mean, there's this huge biological imperative, especially among the youth, to consume sweet things. It's part of their biology. It's important. So you're fighting a really important biological imperative for them to do that. And by that, they feel, obviously that it's not harmful, right? So it's a really good question. How do you get that message across? And it's not just that it's masking the bad things. They may be bad unto themselves, right? They may be harmful agents unto themselves.
How much can the perception be, I guess, manipulated by the context, the advertising material, anticipation? So in terms of, I think this is sort of amplifying Marianne's question. So if you have all kinds of advertising associating sweetness with something good, pleasant.
Right.
So how would that, what do we know about that intersection?
Well, I mean, we certainly know that I have taken, I've done studies in the past where wanting to look at the malleability of responses to chemical stimuli. And what I've done is actually put people in our chamber with the same compound, different groups of people, and characterized it differently in advance. And if I tell them that it's like a botanical and it's coming from, the Amazon and, it has some health properties, they'll sit there for an hour and feel wonderful afterwards. If I take another group of people and tell them that it's a degreasing agent used in certain industries, they'll come out of there with a headache, they'll feel nauseated, they'll be tired, they'll say they were coughing. They didn't, because I've monitored it, but they will exhibit these symptoms. So that expectation is huge in the flavor and fragrance world. It's absolutely huge, because these are very malleable systems from that perspective. What I call the top-down processing, what you think and what you expect is an extremely important driver of what you actually experience.
Let's see, lots, very complicated. Questions? Yes.
Are you planning on doing any cigarette administration research, and what role do you think that would play?
I work with my colleague Paul Weiss, and what has stopped him from suggesting we do that is, in full disclosure, Monell does have some tobacco industry sponsors. We don't take any money from them for the work that we do. I assume they're doing their own work in this area and they don't want anyone else to know about it. But they do provide us with information that we might not otherwise have about, and one of the things that he's been most concerned about is the variability in most of the commercial e-cigarette dispensers that are available. And I don't mean just variability across ones, I'm talking about even within one over time. And so that's why we've used sort of model systems like in nebulizers and other, aerosolizing compounds in a way that we're more comfortable with to assure us that we know what the dose is. But yes, it could happen easily. But as I said, there's just been, I have a colleague who's very persnickety about these things and was convinced by some of our industrial sponsors that we could not get a consistent exposure this way without looking at some other metric of exposure. And so that's why we haven't moved into using e-cigarette products yet.
Could I clarify that? When you say over time, variability over time, are you talking about even over one vaping episode or over months or years?
No, even within a vaping episode, I've been, and again, this may not be every product out there, but I know that they, when big tobacco started getting into the field to, produce their own, this is one of the things they looked at, and they were even having difficulties with their own products in terms of consistency.
Yeah, Jonathan Goldman has been saying that too. It's very tough to study the typology of e-cigarette vaping because no two episodes are the same, or even within one session.
Are there questions or?
Is it able to, could we study the topography of e-cigarette use in situ? So if you have people who puff at different rates, they wait in between frequency and take them as they naturally use a product, can we characterize that well enough in a lab to look at potential differences in inflammatory responses between people who, let's say, puff like crazy or whatever versus others? Can you do that?
Well, it would be nice to have a biomarker of exposure rather than just a biomarker of effect, right? Yeah, I think you need both.
Well, I guess part of my question is, can we take the best metrics that are being used already for cigarette use and like puff volume and so on, as best we can, but not standardizing it to the user.
Right. Let them use it in the normal way,
and see what emerges in terms of whether or not there are different classes of users who, by their naturalistic use patterns, are having more negative effects on inflammatory response than others.
I certainly think that's, certainly one way to go about it. As I said, I would like to have another biomarker of exposure as well, but I think there's also value in understanding the variability in the smoking topography and the puff volume and frequency and all of that. Because for all we know, that's contributing to this variation that might be seen in the population. So I think that's important. Just characterize it, that's all, right? Yeah. I think you said, Jessica, that you were doing some of that as well. Because
Yeah.
it's true that you
Yeah.
have.
I mean, we could certainly look at that. We have data on, I mean, it's very clear that people have very different vaping patterns. And we're getting some inflammatory biomarkers. Could nicotine, I mean, could you not use nicotine as a, I mean, I know it's not perfect in terms of a biomarker of exposure, but, I mean, potentially.
Yeah.
Well, this is really hypothetical.
Go really hypothetical.
Okay, so what if we were to remove menthol entirely from cigarettes? I know there's some menthol in all cigarettes. Is it likely that we'd see a drop in people even starting up smoking?
You would likely see, from what I understand, you'd like to see a drop in certain subpopulations of people starting smoking.
Well, I'd be happy with all populations, but definitely in some populations as well.
Yeah.
I mean, does it really contribute to people being able to tolerate smoking in the beginning if there's even a little bit of menthol in there?
I think so. I think that the evidence is there. But again, you would probably see a bigger effect in certain subpopulations than others because menthol seems to be much more important. And that may be due to some underlying genetic differences that we just haven't been characterized yet. But it certainly might help.
So let me suggest that anybody who wants to go or needs to go, and then those who continue to engage in the discussion while Pamela gets a well-deserved lunch. So, thanks.
All right, thank you very much.
Actually, the question, so my understanding of revelations, et cetera, is that it was very high level, obviously. And then somewhere along the way, they started doing this in low concentrations.
When that started?
That would be sort of.
Yeah, that would be interesting to look at. I think I've seen some tobacco company documents about that probably related, probably sometime in the 80s is when they started.
I don't know, we're just.
Yeah, that would be interesting. Well, it's probably.
Because that would imply that there's a pharmacology on sort of flavor,
Yeah.
the characteristic flavor issue. Because I think, I don't know, I'm not sure we know systematically, that